Welcome back. In the previous session, we have seen what exactly do we mean by computation and how to differentiate between the various computing devices and the other electronic devices. And also, what do we mean by a compute or computation exactly? Also, we had seen the various applications of theory of computer science. So, today in this session, we'll be seeing the syllabus, the course objectives and course outcomes, along with the textbooks and reference books that can be referred by you all. We will be seeing the automata theory definition along with the various basic terminologies that we will be using throughout our entire course and also the definition of finite state machine, that is FSM. So altogether, there are 6 modules out of which 3 are visible on your screen currently. There are basic concepts and finite automata, which is our first module, first topic. And then we'll be seeing the various finite automatas, that is the deterministic finite automata and non-deterministic finite automata, along with the variants of Moore and Millet machines and also the equivalence, applications and limitations of finite automata. In the second module, we'll be seeing the various regular expressions and languages that can be generated using this regular expressions along with the applications. In the third module, we'll be seeing the various grammars, Chomsky's hierarchy and regular grammar which can be created and recognized using the push-down automata. So in this module, that is the third module, we will be seeing context-free grammars, which is an input given to our push-down automata. In the fourth module, we will be actually designing the various push-down automata machines or the mathematical models and seeing the applications of PDA, that is push-down automata. In the fifth module, we'll be seeing the Turing machine, the the machine which is the beginning of our modern day computers. Along with that, in the last module, we will be seeing the various drawbacks and the various problems that occur which come under undecidability due to in the various machines. The course objectives and outcomes were already discussed in our previous session. So we'll just quickly go through it and we'll move on with our actual definition of what is finite automata. Before that, we will be seeing the reference books and textbooks that we can use or refer for this particular course. So textbooks and reference books. One of the most important book that you can refer, which is also known as the Black Book of our course, that is written by author Jeffrey D. Ullman, Introduction to Automata Theory, Languages and Computation. And other than that, we can also use Kavi Mahesh reference book called as Theory of Computation, a problem solving approach. Other than that, Vivek Kulkarni is another good book that can be referred. The notes compiled for this particular course has a combination of all these books, especially Ullman, Vivek Kulkarni and Kavi Mahesh authored books. So what is computation? We had already discussed this in our previous session. So we'll quickly just go through the definition of computation. Computation is nothing but calculating, solving, making decisions or any task done by computer, calculator or any other machine. Then what is theory? In theory of computer science, the term theory defines capabilities, limitations of those machines. And finally, the purpose of the theory of computation. Develop formal mathematical models of computation that reflect real-world computers. That is the whole idea of learning this particular subject. So what is automata theory? Automata theory deals with the definitions and properties of mathematical models of computation. These models play a very important role in several applied areas of computer science. Finite automata is used in text processing, compilers, and as well as hardware design, which we have already seen in subjects such as DLDA. Another model called the context-free grammar is used in programming languages and artificial intelligence. Finally, automata theory is an excellent place to begin the study of the theory of computation. So, beginning with the basic terminologies or the terms that we will be coming across throughout this course is first we have symbol. Symbol is the basic building block of the theory of computer science. Example, it can be anything, small abc, capital ABC, or numbers, numericals such as 0 to 9, etc. The next symbol or the next term is alphabet. Alphabet is defined as the finite set of input symbols and it is represented or denoted with the sigma symbol. For example, input is equal to 0, 1, that is binary alphabet. Input is equal to A to Z and 0 to 9, which is alphanumeric alphabet. And last, input is equal to A to Z, that is alphabet of small letters. Here as you can see that this is a finite set of input symbols. It will end at some point of time, and as it is a set, it is represented within a curly bracket. The next term is string, sentence or word. It is defined as the finite sequence of symbols over the given input alphabet. Example, 01011 is equal to is a string from the binary alphabet input 0, 1. Another example, AB, AC, BC is a string from the alphabet A, B, C. And finally, 3786 is a string over 0 to 9. So it is a numerical. This has alphabets from between only A, B, C, that is a set of input A, B, C, and 0, 1, that is binary alphabet, can generate this string, sentence or word. Either of these three terms can be used alternatively. Next term is string length. It is defined as the number of symbols present in the given string denoted by mod of W. Example, if my W is equal to classroom, then my string length, that is mod of W, will be equal to 9, as classroom string has 9 alphabets or symbol in the string. Next example, W is equal to 010100. Here as we can see there are 6 alphabets or symbols in the string. My mod of W or the string length will be equal to 6. If W is equal to epsilon, then mod of W will be equal to 0. So this just a short note that you need to remember. Empty string is the string with no symbols denoted by epsilon or lambda in some of the books. The next and the final one is language. It is defined as the set of strings defined over the given input alphabet. Language L could be finite or infinite. The rest of the terms that we have seen in our previous pages have finite set. Language L can be finite or infinite. Example, suppose if the input or the alphabet is equal to A, B, then my L1, that is language, will be equal to, if my language L1 is equal to set of all strings of length 2, then AA, AB, BA and BB is the language that will get generated over the input A, B, which is a finite language. Next example, L2. Suppose L2 is supposed to be equal to set of all strings of length 3. Then triple A, AAB, the combinations of AB can, in terms of length 3, will be generated as the language, and it will again be a finite language. Finally, L3 is equal to set of all strings where each string starts with A. Here the language generated will be infinite, as we can have n number of combinations of string that can be generated where it starts with A. Finite state machine. So, finite state machine is defined as it consists of finite set of states S which alter on receiving the input set I to produce the output set O. I'll repeat. Finite state machine consists of finite set of states S which alter on receiving the input set I to produce the output set O. The FSM defines two functions, that is, first one, state function STF represented by S cross I giving us the next state that it should go to, and machine function MAF is defined as S cross I giving us the output that it will generate.